Think about those huge bridges you drive over, or, skyscrapers that seem to touch the clouds, even the pipes in your house.
Yeah, incredible structures.
What holds them all together? That invisible force resisting, well, everything. It's welding.
Definitely. But it's not just slapping metal together.
No, exactly. It's this incredibly precise skill. Art and science, really.
Meticulous standards, deep understanding of materials.
Yep.
It's all engineered.
Right. And today, we're diving deep into that. We want to look at two really key things for safety, for integrity.
Okay.
First, how do welders actually prove they have the skill? And second, this sort of hidden factor called heat input.
Ah, yes, heat input. Crucial.
Apparently, it dictates the weld's strength, its durability. So we'll unpack the standards, the tests, the sheer precision involved using the info from our sources. Let's get into it.
Sounds good.
Okay, so the welders themselves, why is qualifying them so fundamental? I mean, you can't just grab a torch and start working on a bridge, right?
Huh. Well, not if you want it to stay up. No, seriously, the integrity of every single weld is paramount.
Right.
When you're fabricating structures, especially things under pressure, those joints have to be sound. They need the right properties for the job.
Okay.
So welders need to show consistently that they can produce defect-free welds. And they have to prove that before they touch any actual production work.
So it's all about safety, performance, making sure it lasts.
Exactly that.
And I've heard about these things called WPSs, Welding Procedure Specifications, like a blueprint.
Spot on. Think of a WPS as the detailed recipe, the instruction manual for a specific weld.
Okay.
It lays out all the conditions you must follow, voltage, speed, material prep, everything, to make sure the final weld has the properties it needs.
And the welders have to stick to that religiously.
Absolutely. They need to understand it inside out and follow it strictly. And you'll always have welding inspectors on site checking, making sure everyone's working within those specified limits.
Okay, so the WPS is the rule book. How does a welder actually prove they can follow it and make that perfect weld? What's the test like?
It's pretty rigorous. For manual welding, like stick welding, or semi-automatic, like MIG or MAG,
Yeah.
the welder makes a test weld, specifically designed to show they can skillfully handle the electrode or the torch, manipulate it correctly.
So it's about their hands-on skill.
Exactly. Now, if it's more automated, like mechanized or robotic welding, the focus shifts a bit. It's more about proving they can control the equipment properly.
Right, controlling the machine. And someone's watching them do this test.
Oh, yeah. A welding inspector monitors the whole thing, start to finish.
To make sure they follow that WTS.
Precisely. And sometimes, especially for really critical stuff, you might even have an independent examiner, maybe the third-party inspector come in too. Just adds another layer of verification.
Okay, multiple checks. And once the test weld is done, what happens to it? Just looking at it isn't enough, I guess.
No way. That test piece, the coupon, it goes through a whole battery of tests. Non-destructive testing, NDT.
NDT, right.
Yep.
What does that involve?
Well, visual inspection first, obviously. Then things like magnetic particle testing, MT, or penetrant testing, PT. These find tiny cracks on the surface.
Okay.
Then you've got radiography, RT, basically an X-ray for the weld, or ultrasonic testing, UT, using sound waves. These look for flaws inside the weld.
Wow, thorough.
It has to be. Sometimes, depending on the material or the process, you might do some destructive tests too, like bending the weld or cutting it open to look at the structure, a macro test.
But the main goal isn't checking strength here, right? It's about the welder's skill.
Exactly. The main point of the welder qualification test is showing they can consistently make a sound, defect-free weld by following the procedure. The strength stuff is usually covered more by the welding procedure qualification, which is a separate thing.
Got it. So this is pure skill check. And if they pass all that, they get a certificate, like a license.
Pretty much. They get a welder's qualification certificate. It documents exactly what they did in the test, the process, position, materials, everything.
And what they're allowed to do in production.
Yes. Crucially, it defines the range of production welding they are qualified for, based on that test and the standard being used. And often, you'll see it endorsed by that third-party inspector we mentioned. Adds credibility.
Okay, this range of qualification, that sounds important. You mentioned essential variables. What are those? What kind of change would mean they need, more skill?
Yeah, this is where it gets really specific. An essential variable for welder qualification is anything that, if you change it beyond certain limits, might demand greater skill than what they showed in their test.
Okay, so it gets harder.
Exactly. Yeah. The EU standards give good examples.
Yeah.
Like the welding process itself, there's no range there. If you qualify using TIG, you're only qualified for TIG. You can't just jump to stick welding.
Makes sense. Different tools, different feels.
Totally. Then, the type of weld. If you qualify on a butt weld joining two plates edge to edge, that usually covers you for most joints, but not complex things like branch connections on pipes.
Ah, okay.
And if you qualify doing a fillet weld, like in a T-joint, you're generally only qualified for fillet welds.
What about the metal itself?
The parent material type is key too. Your qualification usually covers materials within the same material group number, metals, with similar chemistry and properties, though these groups are a bit broader for welder qualification than for procedure qualification.
So similar metals are okay, but you can't just switch from, say, carbon steel to stainless steel without proving you can.
Generally, no. The filler material, the welding rod or wire, also has a range based on what you used in the test.
And physical stuff, like thickness.
Absolutely critical, material thickness. Welding thin stuff requires very different control than thick plate. For example, a test piece over 12 millimeter thick usually qualifies you down to 5 millimeter for production.
And pipes.
Pipe diameter is another big one, especially small pipes. Below 25 millimeter diameter, the qualification range is really restricted because it takes a lot of dexterity. If your test pipe was, say, 50 millimeter, you might be qualified for pipes down to 25 millimeter.
I can picture that. Welding a tiny tube versus a big pipe.
Yeah.
Totally different. What about the position they're in?
Oh, welding position is huge. Think about welding flat on a bench versus welding overhead, or vertically up a wall, or even vertically down.
Yeah, gravity is not always your friend.
Exactly. So, positions are essential variables. For instance, qualifying at a tricky inclined pipe position like HL0, 4, or 5 might qualify you for most positions, but often excludes vertical down welding, which needs its own specific skill set.
Okay. And one more backing, what's that?
Weld backing. Sometimes you have a strip of material behind the joint to support the molten weld pool, especially for the root pass.
Right.
Welding without backing generally takes more skill because you're essentially forming that root in free space. So if you test with backing, you might not be qualified to weld without backing in production.
Wow. It's incredibly detailed. It really paints a picture of a highly technical skill, not just brute force.
Absolutely. Precision is key.
So once a welder gets this qualification, how long is it good for? Is it like qualified for life?
Definitely not. It starts from the day they weld the test piece, but then it needs to be confirmed every 6 months.
Every 6 months? By who?
Usually by the welding coordinator at their company or whoever is responsible for welding quality. They basically sign off, verifying the welder has been working consistently within the range they were originally qualified for.
And if they haven't been, or if they miss the sign-off?
Then the certificate becomes invalid. Poof.
Okay, so use it or lose it, essentially. Can it be extended beyond that, like for a longer period?
Yes, there are provisions. It can typically be extended for up to 2 years if the welder stays with the same company and that company has a proper quality system in place, like ISO 38342 or Money 3.
Ah, so the company's quality system matters. What if they don't have that, or after the 2 years?
If those conditions aren't met, then a retest is usually needed every 3 years anyway.
Okay. But is there a way to keep it going without retesting every couple of years, assuming they're working consistently and well?
Yes, there's a process called prolongation, but it requires solid evidence.
Like what?
You need records. Records tracing that specific welder to specific WPSs they've used on actual production jobs. Yeah. And this is key. You need proof from NDT, like X-rays or ultrasonic tests, of 2 production welds they've made in the last 6 months before the certificate expires.
And those welds have to be good.
They have to be good. They need to meet the acceptance standards for flaws. And they must have been made using conditions covered by their original qualification. It proves ongoing competence on real work.
That makes sense. It's continuous verification. But what if a welder starts having problems, like making bad welds in production?
Well, the certificate can be withdrawn. If there's good reason to doubt their ability, maybe their prepare rate spikes or they're caught consistently not following the WPS, then their qualification can be pulled. Safety comes first.
Right. The whole system depends on trust and proven skill.
Okay, so we've got the welder's skill covered, proven, tested, maintained. But you mentioned even the best welder needs the physics controlled, which brings us to heat input.
Yes, heat input, a critical, sometimes overlooked factor.
What is it exactly, in simple terms?
It's basically the amount of energy the welding arc delivers to the workpiece measured along the length of the weld. The standard unit is kilojoules per millimeter, kilomillimeter.
Kilojoules per millimeter. Seems like a tiny unit for such big structures.
It is, but it has a massive impact on the final properties of that weld metal.
Now, I saw our sources make a distinction. They talk about arc energy and heat input. Are they different?
They are related, but different. Good catch. Arc energy is the energy generated right at the arc, per unit length of weld.
Okay, the raw power. How's that calculated?
Simple formula. Volts times amps, divided by the welding speed in millimeters per second times 1,000. That last bit just gets the units right into kilojoules.
Volts x amps, speed by 1,000. Got it. So that's arc energy. What's heat input then? Heat input takes the arc energy calculation and then multiplies it by something called the thermal efficiency factor, usually written as K.
Okay, K, what does that represent?
K tells you how much of that arc energy actually makes it into the metal to do the work of melting and fusing. See, not all the energy from the arc goes into the weld pool. Some gets lost to the surrounding air, radiation, spatter.
Ah, so it's an efficiency rating for the process.
Exactly. And different welding processes have different K factors.
Like what? Give me some examples.
Sure. Submerged arc welding, SAW, where the arc is buried under flux. Very efficient. Its K factor is 1.0. Basically, all the arc energy goes into the workpiece.
Wow, 100% efficient.
Pretty much. But common processes like stick welding, MMA, or MIG and MAG welding, their K is typically 0.8. So only 80% of the arc energy becomes heat input.
Okay, and other
Processes like TIG or plasma arc welding, they're even lower, around 0.6 or 60% efficient. So knowing the K factor for your specific process is vital to get the actual heat input right.
That's fascinating, but why? Why go to all this trouble calculating precise heat input? Isn't just melting the metal enough? Why does the exact amount of energy matter so much?
Because heat input directly controls the cooling rate of the weld. And the cooling rate determines the final microstructure of the weld metal and the adjacent base metal, the heat effective zone, or HAZ.
Microstructure, like the tiny crystal structure inside the metal.
Exactly. And that microstructure dictates the mechanical properties, especially things like toughness, the ability to resist fracture, particularly at low temperatures, and hardness.
So messing up the heat input means you mess up the toughness or hardness.
Precisely. Too much heat input leads to slow cooling, which can result in a coarse-grained structure, potentially low toughness, maybe too soft. Too little heat input means very fast cooling, which could make the weld too hard, too brittle, and maybe prone to cracking.
Okay, so it's a balancing act.
It absolutely is, and the standards reflect this. There's often what we call the 25% rule.
The 25% rule. Tell me more.
Well, if toughness is a critical requirement for the weld, say, for something used in cold environments, the maximum heat input you're allowed in production is typically only 25% higher than the heat input used during the procedure qualification test.
Okay, so you can't go too much hotter than the proven value.
Right. Conversely, if hardness is the main concern, maybe you need wear resistance, but don't want it too hard and brittle, the minimum heat input allowed in production might be restricted to no more than 25% lower than the test value.
Wow. So there's this really quite narrow window, this Goldilocks zone for heat input to ensure you get the properties you need.
That's a perfect way to put it. It's not just about melting, it's about carefully controlling the thermal cycle to engineer the desired material properties in the final weld.
Let's try a quick calculation, maybe using that example from the sources, just to see it in action.
Sure. Let's take a mag weld. Say the parameters recorded were arc voltage, 24 volts, welding current equals 240 amps, and the travel speed equals 300 millimeters per minute.
Okay. First step. Speed needs to be in millimeter per second.
Right. So 300 millimeters divided by 60 seconds per minute. That's 5 millimeters per second. Easy enough.
Okay, 5 millimeters. Now, arc energy, that was volts times amps divided by speed times 1,000.
Yeah. So 24V240A divided by 5 millimeters 1,000. That's 5,760 divided by 5,000.
Which comes out to 1.152.
1.152 kilomillimeter. We can probably round that to 1.2 kilomillimeter for simplicity here.
Okay, 1.2 kilomillimeter arc energy. Now, the actual heat input, we need the K factor.
Right. For mag welding, we said K is 0.8.
So it's 1.2 kilomillimeter times 0.8.
Which gives us 0.96 kilomillimeter.
0.96. That tiny number dictates so much about whether that weld will perform safely. It's incredible.
It really is. It highlights the level of control and understanding required in modern welding.
So wrapping things up today, we've really unpacked the human skill side of welding with qualification, how vital it is that welders prove their ability, follow the rules, the WPS, and keep that skill verified.
Through rigorous testing and ongoing checks, yeah. It's built on demonstrated competence.
And then we dove into this less visible but equally critical factor, heat input. Not just melting metal, but precisely controlling energy to engineer the right properties. Toughness, hardness.
That Goldilocks zone, controlled by calculation and careful monitoring using things like that K factor and the 25% rule, it ensures the weld is fit for purpose.
What really stands out, I think, is just the layers of precision behind something that seems so fundamental, maybe? Welding, it's not just sticking stuff together.
No, it's applied material science, engineering, and skilled craftsmanship all rolled into one, governed by these really detailed standards.
It makes you think, doesn't it? Considering this level of detail for welding, what other hidden engineering, what other quality controls are going on all around us?
Right. In the buildings we use, the cars we drive, the planes we fly in, countless invisible checks and balances, quietly keeping things safe and working that we just never see.
Definitely something to ponder next time you look at a bridge or a building.